Poynting's theorem. Poynting's theorem is the work energy theorem of electrodynamics. It states that the work done on the charges by the electromagnetic force is equal to the decrease in energy stored in the field less the energy that flowed out through the surface. And the energy per unit time, per unit area transported by the field is called the Poynting vector, and it can be represented as S is equal to 1 by mu 0 E cross B. So we can derive this Poynting's theorem. So an electromagnetic wave consists of an electric field and magnetic field which can independently store energy. The energy stored in an electric field, the energy density stored in an electric field can be represented as U is equal to half epsilon 0 E square. Similarly, the energy density stored in a magnetic field is UB is equal to 2 mu 0 B square. Therefore, the total energy stored in an electromagnetic field is given by, that is, U is equal to UE plus UB, or it can be represented as half epsilon 0 E square plus 1 by 2 mu 0 B square. This is the total energy stored in an electromagnetic field. So we are considering a system of charges which can produce an electric field E and a magnetic field B. So let a small charge Q. It is moved through an infinitesimal distance dl in a time dt. Then according to the Lorentz force law, the force acting on the charge we can express F is equal to Q into E plus V cross B. This is the Lorentz force. Then the corresponding work done on the charges Q due to the displacement dl can be written as the work done dw can be written as dw is equal to the force into the displacement, where dl is the displacement made by this small charge Q. So this can be represented as force is this one, Q into E plus V cross B dot dl. So this dl can be represented as dl is the small displacement made by the charge Q in a time dt. So this can be represented as, that is, the velocity V is equal to displacement by time, or dl can be represented as V into dt. So this can also be written as, that is, this is equal to, the first term will be Q into E dot V dt, and the second term is V cross B dot V dt. But we know that V cross B is that in the case of a magnetic force, if this is the velocity of the particles and this is the magnetic field, then we can represent this force as the perpendicular to, that is, this is V cross B. This is V and this is B, then force will be this direction, in this direction. It will be in this direction. This is the force. So this force will be perpendicular to the V. And V cross B, this gives force, and this force is perpendicular to V. So we can say there will not be, the particle is moving in this direction, and there will not be any displacement of the particle along this direction, that is the direction of the force. So this term, it will be 0, that is V cross B dot V dot T, it will be 0. That is, the idea thinks is that the magnetic force do not work. That is, the magnetic force do any work, that is this V cross B dot V dt. So this will give dw is equal to Q E dot V dt. And we can consider the rate at which the work is done on the charters in a volume V. The rate at which the work is done on the charters in a volume V, we are considering this, that is the dW by dt. So we are considering over a volume, this can be represented as E dot J into d2. d2 is a volume and is the field and J is the current density. So this E dot J, it is the work done per unit time per unit volume, or we can represent this as the power delivered per unit volume. So we can represent this quantity in terms of the electric field E and the magnetic field B using the Ampere-Maxwell's equation, and we can eliminate this J. That is, the equation is E dot J is equal to 1 by mu 0 E dot del cross B minus epsilon 0 E dou E by dou T. Dou E by dou T. We can represent this. That is, this to eliminate J, we can represent this equation in terms of E and B. But we know that this del dot E cross B is equal to, we can use a vector identity, that is del of A cross B, where A and B are any two vectors. We can represent it as B dot del cross E minus E dot del cross B. This is the representation of del dot E cross B according to del of A cross B notation. So this can be represented, we can rearrange this, that is del of E cross B is equal to B of del cross E minus E of del cross B. But from Faraday's law, we can write that this del cross E is equal to minus dou B by dou T. Del cross E is equal to minus dou B by dou T. So B dot del cross E, this equation, it can be represented as minus B dot dou B by dou T minus B dot dou B by dou T. Then again this term, that is E dot del cross B, can be represented as, that is E dot del cross B can be written as B dot del cross E minus del of E cross B. That is, this E dot del cross B can be written as this from this equation. It is this B dot del cross E minus, this will goes to the right left hand side and this will go to the right hand side, minus del of E cross B. But this term B of del cross E, according to Faraday's equation, del cross E is minus dou B by dou T. So this equation will be leads to minus B dot dou B by dou T minus del of E cross B. This equation. But we can represent this B dot dou B by dou T as equal to, that is 1 by 2 dou by dou T of B square. We can represent this term as B dot dou B by dou T is equal to 1 by 2 dou by dou T of B square. And similarly we can write E dot dou E by dou T is equal to 1 by 2 dou by dou T of E square. So we can substitute this equation, and also the substitution into this equation. E dot J is equal to 1 by mu 0 E cross del cross B. Then the E dot J becomes, we are making all the substitution, So E dot del cross B, we can substitute from here E dot del cross B from this equation, and instead of this equation epsilon 0 E, we can write this one, E into dou E by dou T, this time E into dou E by dou T half this one, and rearranging we get, that is E dot J is equal to half minus half dou by dou T of this epsilon 0 E square plus 1 by mu 0 B square minus 1 by mu 0 del dot E cross B, del dot E cross B. So we are here in the second term. So this E dot J, we can substitute this E dot J into this equation, that is dW by dt is equal to volume integral E dot J dt. Here we are substituting the value of E dot J from this equation. Then it will be dW by dt, that is dW by dt is equal to E dot J within this volume. So substituting the value of E dot J from this equation, and here the volume integral E dot J, this quantity. In the second term we get this quantity. So here the volume integral 1 by mu 0 del of E cross B can be converted into surface integral according to this divergence theorem. So then the equation will becomes dW by dt is equal to minus d by dt volume integral half epsilon 0 E square plus 1 by mu 0 B square into dt minus, that is 1 by mu 0 surface integral, instead of the volume integral, surface integral E cross B dot dA, where S is the surface bounding the volume and dA is the infinitesimally small surface. So this is the actual Poynting's theorem, state that, and instead of this value we can write E cross B as the S, that is Poynting vector. We can represent this 1 by mu 0 E cross B as the Poynting vector. Then we can rewrite this equation as dW by dt is equal to minus d by dt of volume integral this term. This is the total energy density, that is the total energy density we can represent from this equation U, that is volume integral U dt minus the surface integral S, where 1 by mu 0 E cross B is the S, Poynting's vector, S dot dA, that is, this is the Poynting theorem. It states that the work done or the rate of work done on the charges by the electromagnetic force is equal to the decrease in energy. This is the decrease in energy stored in the electromagnetic field. This is the energy stored in the electromagnetic field, less the energy that flows out of the surface. This is Poynting's theorem.